Welcome to a new session, Principal Stress and Strain. So first of all, what is principal plane and principal stress? So plane is those planes on which only normal stresses act are called principal plane. That's a basic definition. And the normal stress that acting on that particular principal plane is called principal stress. That's a total definition. So in order to find out the principal plane and the principal stresses, we have to find out the relation between stress acting on plane with inclination. For any arbitrary plane theta, we need the values. So first of all, we start with the stress analysis. So stress analysis is concerned with the stress acting on some arbitrary plane due to external loading. Suppose on this three-dimensional object, stress sigma is acted along the longitudinal direction. So let be sigma. So I want to analyze what will be the stress acting on the plane which is inclined to the vertical by an angle theta, some arbitrary plane. So I can draw like this in three-dimensional case. So what will be the normal stress or shear stress acting on this particular plane? Let A be the area cross section on the longitudinal direction. The force F acting on the longitudinal direction we can find out using sigma into A. So I can resolve this force F which is acting on the plane along its perpendicular direction as well as along its surface direction. So the component of force normal to the surface, I can say sigma A is the total force into sine theta. Since angle between these two parts is theta, therefore definitely the angle between the perpendicular of these components. So this is the side perpendicular of this component going to this direction, longitudinal direction, and perpendicular for this slanted surface going to be this. So this angle will be theta. Definitely F can be resolved as F cos theta. So the normal component will be F cos theta. Then we have to find out what is a normal stress acting then. Definitely normal stress acting will be normal force acting divided by normal area. So A is the area cross section along the perpendicular longitudinal direction. So if this slanted area is A dash, we can relate that A dash is nothing but A by cos theta. And another way we can say A is this and the component of A is given as A dash is the A value. Definitely A dash can be written as A cos theta. Therefore the normal stress we can write now sigma divided into area, that is a corresponding force, into cos theta divided by area, that is A divided by cos theta. So A get cancelled, therefore sigma n becomes sigma cos square theta value. In similar way, the shear stress acting or the tangential stress acting on the surface can be taken as the tangential component of force Fg divided by area A dash value. So that going to be sigma A sin theta divided by A by cos theta. So A get cancelled, you will get sigma into sin theta cos theta. In another manner, you can write sigma by 2 into sin 2 theta. So for this small example, we can find out the principal plane. So principal plane is a plane where the shear stress is 0. So we can either find out using this method. Tau is assumed to be 0 at some particular angle theta. So this is equal to sigma 2 sin 2 theta. Definitely sin 2 theta should be 0. So we can say 2 theta should be some multiples of integer multiple of pi value. So when n equal to 1 value, theta going to be pi by 2 or 0, pi, etc. So that will be the solution for shear stress going to be 0. Now substitute this theta value for sigma n. Sigma n is equal to sigma into cos square 0 value, that's going to be sigma. So the plane where tau is going to be 0, we find out that at angle theta equals 0, pi by 2, pi, etc. So the pi equal, or the angle theta is goes to 0 means nothing but the vertical plane itself. It's obvious that only normal stress is acting, shear stress is 0. So this is the one of the principal plane. Another principal plane we can find out when theta is going to pi by 2. So theta going to pi by 2, that's a plane, this one, or any horizontal plane here we can consider, where the tau is 0, normal stress going to be value. So at pi by 2, sigma n value goes to 0. At theta equal to 0, sigma n value go to maximum sigma. So there are two principal stresses, while one is maximum and another one is minimum. So these are the principal stress denoted by sigma 1 and sigma 2. This is a maximum and sigma 2 is a minimum principal stress. So another method to find out the maximum principal stresses, maximum minimum principal stresses, using the idea of application of derivative. Sigma n, we find out that is sigma into cos square theta value. So sigma is varying as a function of theta. So if you take derivative sigma n with respect to theta and equated to 0, you will get that 2 cos theta sin theta, that's going to be 0. So corresponding theta value will be for maxima or minima value. So here 2 times sigma minus, okay, minus. If we take the 2 inside, we can say that 2 sin theta cos theta is nothing but sin 2 theta equals 0. Similarly, sin 2 theta going to be 0, definitely theta value going to be n pi by 2 value. So was the value of n 0, 1, 2, etc. You will get different planes. That's a method of solution. So previous case was all a simple one. Now coming to another case that more complicated. There is a normal stresses sigma x as well as sigma y, and shear stress are also acting on a plane or two-dimensional object. Okay, here stress acting on an arbitrary plane which is making an angle theta with the vertical side is found out using a transformation equation, that is sigma n value, which is a normal stress acting on that particular plane, n is given by sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta value. And the shear stress acting is given by minus of sigma x minus sigma y by 2 sin 2 theta plus tau xy cos 2 theta value. So in order to remember this equation, first of all you have to understand what is the sign convention we followed. Over the tensile stress is taken as positive. That's the first thing you have to consider. Sigma x, this is acting in the tensile action. It's trying to elongate the body. Definitely that kind of stress is taken as positive. And coming to shear stress, there is two conversion for this. In this particular figure, we use this kind of shear stress. So shear stress is applied, the complementary stresses are developed at the opposite sides. So this kind of stress actually is considered as positive. This is a sign convention we are following. And another kind of loading, suppose the shear stress is like this, we will consider it as a negative. Only two options are available for plane stress condition. So this is positive and this is negative. So according to that, if this is a condition, if the second figure is a condition, you have to replace tau xy with a minus tau xy here and here also. If sigma x is positive, okay, this equation is valid, and tau xy is this kind of configuration, this is valid. Otherwise you have to interchange the sign. Now we can discuss how we can find out the principal plane and the principal stresses. So from the transform equation, we find out that tau xy acting on an arbitrary plane theta with the vertical, which is given by this formula, minus sigma x minus of sigma x minus sigma y by 2 sine 2 theta plus tau x by cos 2 theta value. So we know that the principal plane is a plane where shear stress is 0. So we can equate this value into 0. Therefore, definitely this quantity becomes minus sigma x minus sigma y divided by 2 sine 2 theta plus tau xy cos 2 theta value. If we rearrange that, we will get a formula that tan 2 theta is equal to tau xy 2 tau xy divided by sigma x minus sigma y value. So we got the plane where the shear stress is going to be 0. So our triangle will be look like this. So if this angle is 2 theta, definitely the opposite side will be tau xy and adjacent side will be sigma x minus sigma y by 2. Definitely the hypotenuse will be going to be root of sigma x minus sigma y divided by 2 the whole square plus tau xy whole square value. So for that particular plane, we find out the theta value. If we substitute the value for cos 2 theta and sin 2 theta, we will get an expression for sigma n. We will get the expression sigma 1 comma 2 is equal to sigma x plus sigma y by 2 plus or minus root of sigma x minus sigma y by 2 whole square plus tau xy whole square value. So if we get the plus value, you will get the maximum principal stress, that is sigma 1. And if you take the negative, they will get you the minimum principal stress. So in another portion, we have to cover that is the maximum shear stress acting plane. So definitely the maximum shear stress expression is given by tau n is equal to minus of sigma x plus sigma y by 2 sine 2 theta plus tau xy cos 2 theta value. So if you want to find out the maximum value, we have to take derivative of shear stress tau value, tau xy or tau value with the theta equal to 0. So we will find out that the maximum shear stress going to be root of sigma x minus sigma y by 2 the whole square plus tau xy the whole square value. And that maximum plane will be tan 2 theta equal to minus sigma x plus sigma y by 2 sigma x minus sigma y divided by 2 divided by tau xy. So you have to remember that the principal plane and the maximum shear stress plane will be always subtend an angle 45 degree between them. And the principal planes, maxima and minima planes will be between angle of 90 degree. For example, in this case of uniaxial loading, the maximum normal stress, principal stress, which was at the plane theta equal to 0, that was this plane. And the maximum shear stress will be at an angle 45 degree with the principal plane. So 45 degree we can draw like this. We can draw like this. So this is the plane where maximum shear stress going to act, and minimum principal stress that's going to be acting at a plane which is horizontal. We know that value 90 degree apart from the vertical. So between the principal planes there is a 90 degree shift, and between the between the principal stress and maximum stress there will be 45 degree inclination. 45 degree inclination. Suppose there is a biaxial loading, sigma x and sigma y is acting. The principal stress we can find out sigma x plus sigma y by 2 plus or minus root of sigma x minus sigma y by 2 whole square plus tau xy square. Here there is no shear stress, this is going to be 0. So answer will be sigma x plus sigma y by 2 square root of this square value, we will get the sigma x minus sigma y by 2 value. So if we take the plus sign, we will get sigma x going to be the maximum value, and sigma 2 become corresponding sigma y. If sigma x is greater than sigma y value, we can say this is the maximum and sigma 2 is going to be the minimum value. Now come to the problem. So sigma x is acting at this plane. So this is the first principal plane, and this is a sigma y is acting at this on this plane, perpendicular to this plane. So definitely that going to the minimum principal stress plane. Okay. Now considering the maximum shear stress plane, that is tan 2 theta is equal to minus sigma x minus sigma y divided by 2 tau xy. Since shear stress is 0, this is going to be 1 by 0, so going to infinity. Definitely 2 theta will be 90 degree, so theta will be goes to 45 degree. Definitely the maximum shear stress plane will be 45 degree with the vertical plane. So between principal normal stresses, principal stresses is 90 degree, and with the maximum shear stress, both planes making 45 degree each. So majority of the question actually came from this portion, that is the principal stress and strain from the Morse circle portion. That's a graphical analysis that we'll discuss in another session. So in this session, we are discussing a question which was asked based on the analytical method of solving stress and strain. So here, the question 2015, around 7 questions asked in 2015 from the principal stress and strain portion. So this question was asked in 2015. So a system under biaxial loading induces principal stress of 100 Newton per centimeter square tensile and 50 Newton per centimeter square compressive at a point. The normal stress at that point on the maximum shear stress plane is. So we want to find out what's the normal stress at that point on maximum shear stress plane. So definitely maximum shear stress plane for a biaxial loading, we discussed that will be at a 45 degree with the vertical. So that is a basic knowledge you have to know to do this problem. Since the angle is obtained, we can go to the direct equation. The normal stress acting on any arbitrary plane is given by sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cos 2 theta plus tau xy sin 2 theta. So the sign convention you have to remember. So this equation is actually came from this particular kind of loading. Here tau xy is not there, only biaxial loading they are saying. Therefore this is going to be 0. Next section, sigma x sigma y. We know the sign convention that for a tensile load we consider as a positive. Here 100 Newton per centimeter square is tensile and 50 Newton per centimeter is going to be compressive in nature. Definitely we have to consider that sign conversion. Please note that it's not going to be centimeter square, everything in mm square. Please take it as considered. Now come to the question, sigma x, we are taking sigma x going to be 100 and sigma y that's going to be minus 50 because that's a compression. So here 100 minus 50 divided by 2 plus 100 minus of minus going to be positive divided by 2 into cos 2 theta. Theta definitely 45 degree. 2 theta 2 times 45 going to 90, cos 90 going to be 0 value. So rest of the value we get 50 divided by 2, that is 25 Newton per mm